Okay, hello good people. Today we are talking about permanent magnets and magnetic fields. And now let me get this nice and big so I can show you some things. Here in front of me I have some magnets right here. These magnets, I also have some paper clips over here, and I also have a nail, and I also have a copper wire. Now, if you were here, then what I would do is I would say, okay, can you play with these magnets a little bit? And I would ask you to find a few different things. Here's what I would ask you to take a look at. First, I would say, hey, do you notice that the strength of the magnetic field between these two magnets, the strength of the force that's pulling them together, do you see that that depends on distance? And probably you understand this from your past experiences, that if you take two magnets and you hold them far apart like this, at first the pull between them is very weak. But as you get closer and closer and closer, you can feel them pulling on each other harder and harder and harder until you get close enough and they go. I also would ask you questions like, hey, is there anything that makes them, is something like the number of magnets, does that make them stronger or weaker? And what you'd do is you'd hold up two little magnets like this, much less than before, and you'd say, whoa, they still seem to pull together, and they still seem to be just as hard to pull apart. And you would say it's interesting because it feels like it's the same difficulty to pull apart 6 magnets as it is to pull apart, wait for it, as it is to pull apart 2. So you'd say, no, it seems like the number of magnets doesn't actually matter for their strength. Then I would ask you a few other questions. Like I would say, is there any way that you could block a magnet? And you'd say, well, maybe if I put something that was like not magnetic in between the magnets, then maybe that would make it not be magnetic anymore. Like, for example, if I took this piece of paper here and I stick this piece of paper between the two magnets, but oh, nope, they still stick through the piece of paper. Really, they'll still stick through a lot of things. Like they'll even still stick between my fingers like this. The only thing that makes it so that they get blocked from each other is if I increase the distance really significantly so that they can't really see each other anymore. They can't feel each other anymore. They're so far apart that that magnetic force is weaker. But there's nothing that I can put between them that makes the magnetic field not there anymore. So that's another thing you would notice. And then you would notice something like this. You would notice that not all materials stick to the magnet. You would say the nail definitely does stick to the magnet here. You would say the paper clips definitely do stick to the magnet and they don't fall off. But you would say, but not everything is that way. You would say, oh, well, paper clips sticking to the magnets in my computer. You would say this piece of paper doesn't stick to the magnet at all. So you would say there are some things that stick to the magnet and other things that don't stick to the magnet. And those would be some observations that you would make. Today we're going to talk about magnets, and we're going to talk about permanent magnets, which is what you see here. These are what we call permanent magnets, and then we'll talk a little bit about magnetic fields. Let's go ahead and get started. I'm going to shrink that back down. Okay, let's do it. First, the first question that I want you to answer is, what is a magnet? What is a magnet? Well, let's start here. You know that there are 4 fundamental forces in nature. And those 4 fundamental forces are gravity. Let me write all 4 here. Gravity is the weakest. The nuclear strong is the strongest. Then we have what we call the nuclear weak force. And then we have this other force that we call the electromagnetic force. Now, last unit, in all of Unit 10, we talked about the electromagnetic force, but we really primarily concentrated on this electro part of the electromagnetic force, the electricity part. And we talked about the electrostatic force and how the electrostatic force works and what it depends on and all of those kinds of things. Well, today we're going to talk a little bit about this magnetic half of, we're going to talk a little bit about the magnetic half of the electromagnetic force. And when we talk about the magnetic part, here's what I want you to see is that we consider electricity and magnetism to be so closely related that we say that the magnetic force, which really is like the force that pulls these two little, the force that pulls these two little magnets towards each other, we say that force is in the same family. It's so deeply related to the electric force, which is the force that pushes electrons apart or pulls protons and electrons towards each other. We saw that those forces are so deep down related that they're almost two sides of the same coin. We'll talk about why that is and how that's true, especially as we get later into this unit, because this unit is all about magnetism and electromagnetism, and we'll talk about how electricity and magnetism are related. But for today, all that you need to know is that they are deep down related. And you'll see that here when we talk about what causes magnetism. Here's your fun fact of the day. This is the most important conceptual takeaway of anything that we'll do in this video today, is to understand that all magnetism is caused by moving charges. All magnetism is caused by moving charges. And that is a huge conceptual idea that will carry us through like the whole rest of the unit. So make sure that you write this down. I would like put it in a box, put a star next to it, highlight it, something so that you know that this is important, that all magnetism is caused by moving charges. Here's the idea. You know that a gravitational field happens in space if there's something with mass in space, because mass creates gravitational fields. You also know that if I have a little charge sitting in space, then there's an electric field around that charge, because charge creates an electric field. Well, magnetic fields are caused by moving charges. If you have a charge that is moving through space, that little charge moving through space will create a magnetic field. So any magnetism that you see is the result of moving charges. Now, this is the point in time where most students take a look at me and they say, but wait a second, Miss Wilson, that magnet doesn't really look like it has a lot of moving charges going on. It looks very stationary. I'm not seeing it's not like current running through a wire where you see like little moving charges, like little electrons running in their little directions. No, this is just like a little piece of magnet that is just sitting there. And they say, I don't really understand, Miss Wilson, where that comes from. Well, here's the truth. And 1 second here, I'm actually having some glitchy issues, so I'm going to pause this really quick and then I'll come back. Okay, so here's the truth, is that all magnetism is caused by moving charges, which means there have to be moving charges inside of this magnet. And there are. This magnet is made up of atoms, and I'm going to draw a picture of an atom here. Let's make some little positive charges. Here's some little protons in my nucleus. I'm going to make a little lithium atom here. So I did 3 little protons and 3 little neutrons for my particular isotope. Here's a little lithium atom. Let's make a nice circle for a little orbital situation here. Here's another circle where we got more electrons because our first little shell is going to be filled. I have 1 little electron sitting right here. Kind of hard to see it actually. Let's redraw that. Kind of like this. Oh, nope, not the outside circle. Please return outside circle. Darn it, did I lose it? Ah, tragedy. Okay, here's my outside circle. You can imagine this outside circle has looked better before, but that's okay. Okay, here's an electron. Here's another little electron over here. And here's my 3rd little electron. And this is my little lithium atom. Okay, here's the idea. This lithium atom does have charges. It has some positive charges in the middle, and it has some negative charges going around the outside. And it does have moving charges. For the most part, these positive protons right here are pretty stationary, but these electrons, we know a few things about them. First, we know that they are zippy-zapping all around the outside of this atom, kind of like crazy-like. And we also know that electrons have a property that we call spin. Now, I should not, please don't tell anybody that I told you this, that I told you that electrons are spinning on their little axes, because it's not true. Electrons don't spin on a little axis, kind of like how the world rotates around its axis. That's just not how electrons work. But we do talk about how electrons have a property called spin, and you can actually think of it as the electron spinning. It's a really nice analogy that you can think of, even though it's not totally true. So you can think of these electrons as kind of orbiting around the nucleus of the atom, and you can also think about them as kind of spinning around on their own axes, which again, not totally true, but you can think about it that way. Regardless of how you think about it, the truth is that these electrons are in fact moving. So you have moving charges. which means that each little electron, because it's a charge moving in space, it is creating a magnetic field. But normally what happens is this little electron would move like this way, and this little electron would move this way, and this little electron would move this way, and they'd all be going different directions. And because they're all going different directions, well, they'd each be making their own little magnetic field, but those little magnetic fields would cancel out because they're all going different ways. But if all the little electrons were all marching in the same direction together, then their magnetic fields would add together. And if all the little electrons were marching in the same direction, if they were all lined up in the direction of their motion, then this little atom would act like a tiny mini magnet because it's made of moving charges. An atom that acts as a mini magnet is what we call a dipole. Whoa, my writing was very crooked. It's what we call a dipole. A dipole is an atom that is acting as a mini magnet. It's one atom that acts like a magnet because all of the electrons are moving in the same direction. A dipole is one atom that acts like a magnet because all of the electrons are moving in the same direction. If you didn't get that, that is a definition, and I would write it down in your notes that a dipole is like a mini magnet because all of the little electrons are moving in the same direction. It's a one atom sized magnet. Now, here's what you could imagine, is you could imagine that this little magnet right here, wait, I keep having to strip all the paper clips off it. You could imagine that this little magnet right here is made of atoms, and those atoms are acting as little dipoles because all their electrons are spinning in the same direction. But it's not quite enough to just have a bunch of dipoles in here. Let me show you what it has to look like. I gotta get a brand new page here, so let's get that all queued up. Okay. Here is a zoomed in picture of what we shall call an iron crystal. Here's a little crystal of iron. Now, here's the truth, is that, and this is the weird thing about magnetism, but magnetism is contagious. And what I mean when I say that magnetism is contagious is I mean that if you have something that's magnetic, it'll cause other things to also be magnetic. That means if you have a little dipole with little electrons spinning around, those little electrons will create a magnetic field. And if any other electrons happen to wander by, well, the electrons that are creating a magnetic field will make the other electrons start to march in the same direction. And so if the first electrons are marching in a direction, creating a magnetic field, now the other electrons are marching in a direction, creating their own magnetic field. And then if another electron happens to wander in, then it'll start marching in the same direction because it'll be forced by the magnetic field. And then if it's marching in the same direction, then it's creating a magnetic field. So magnetism is contagious. If electrons are all marching in one direction together, then and another little electron walks by, that magnetic field will push on that little electron and try to make it line up with the rest. It's kind of like how here, I'll show you with my magnets here. It's kind of like, you can see this on a very big scale here. If I have these two magnets like this and I flip this one so that it's facing whoop like this the other way, this is the way that magnets go when they don't want to be close to each other. And if you were here, you could feel, whoa, gosh, you could feel that these two do not want to be friends with each other. They do not like each other. But if I let this thing go, oh, that was so fast. I hope you could see it and it wasn't too glitchy and that you could actually see it happen. If I let this buddy right here go, oh gosh, oh, well, okay, that was just me doing a bad job. But if I let this thing go, it'll actually flip around and get lined up with the other magnets. Magnets will try to make other magnets get lined up. So here, it's out of line. Everybody's facing the wrong direction. To make it get back in line, it'll literally put a force on it that turns it back into place. Same thing will happen with electrons. If the electrons are marching in the wrong direction, but then they pass by a little dipole, those electrons will create a magnetic field that'll push those electrons so that those electrons are going the same way as everybody else. This leads to something very interesting that happens inside of a little magnet, and let me show you here in our little picture. Here I have a little iron crystal. Well, what's going to happen inside of this iron crystal is there's going to be a little clump of atoms. I'll draw a little clump of atoms down here. a little clump of dipoles. And because those dipoles are all right next to each other, they're all influencing each other. And so they're all making the electrons spin the same direction. So the atoms are all making, let's say that in this little cluster right here, in this little cluster, you have a bunch of atoms and all of their electrons are all moving that way. They're all marching that way. Well, because they're all marching that way, they're making all the neighborhood dipoles also march this way, so all of the dipoles are lined up in this area. Then you could have another little area, like let's say like up here, in this little area, you would have all the dipoles are influencing each other, so all of their little electrons are lined up and all their little electrons are marching this way. Then you could have another area like this area, and in this area you could have all the little electrons marching up this way. Then you could have another little area like in this little clump. In this little clump, all the dipoles are lined up, and all of the dipoles are marching, let's say, this way. And so on and so forth. You would have all these little clusters, and in the little cluster, all of the little electrons in that cluster would all be marching the same way because the dipoles influence each other, and the dipoles make little clusters of dipoles where all of the dipoles who are in that cluster together are all marching the same way. These little clusters of dipoles here are what we call domains. A domain is a cluster of dipoles that all have their electrons moving in the same direction. That's a domain. Now, this little picture of this iron crystal right here, this iron crystal is not magnetized because this little dipole has all of its electrons going this way. This little dipole has, or this little domain, sorry, has all of its electrons going this way. This little domain has all of its electrons going this way. This little domain has all of its electrons going this way. So they're all creating magnetic fields, but all their magnetic fields are random, and so they're all canceling out. If you wanted a piece of iron that was slightly magnetized, here's what you would need. You would need a piece of iron, whoops, let's try that again. You would need a piece of iron in which the dipoles are a little bit more, or the domains, excuse me, are a little bit more lined up. Like if you had something like this, for example, so sorry, excuse my poor drawing. If you had something like this, for example, do you see that all the domains are pointing in the same general direction? Now, almost all of the electrons in this whole substance are going in the same direction. And so, we would say here that this is slightly magnetized. And this is what a magnet looks like. If you look on the inside, you would see that all of these little electrons are all moving in the same direction together, and we would say that it is a magnetized piece of iron because all the domains are aligned. If you wanted a super magnetized magnet, if you looked inside of it, you would see that all the domains look something much more like this. All of the domains, notice, are super lined up here. This would be a strongly magnetized piece of iron. The strength of a magnet depends only on the alignment of the domains in that magnet. If the domains are super lined up with each other, then you have a very strong magnet. If the domains are slightly aligned but not totally aligned, then you would have a slightly magnetized magnet. And if the domains are not at all aligned, then you don't have a magnet there, you just have a piece of iron. All that you have to do, here's the question that students ask, is students ask, okay, Miss Wilson, how do you get the domains to get lined up? Well, all that you have to do is put the piece of iron in a magnetic field. Magnetism is contagious. And so if you put it in a magnetic field and that magnetic field is pushing all the domains and saying, hey, everybody go this way, hey, everybody spin this way, hey, everybody spin this way, then all the electrons will start spinning that way. So all you have to do is put it in the presence of a really strong magnet. I'll show you an example. Let me make this big. Hang on, 1 second. 1 second, folks. Just a moment here, please. Okay. Here I have a nail that is attached to my magnets. And then here, I have a paper clip hanging from the end of the nail. Sorry. Why does the paper clip not fall off? Is it because the paper clip is attracted to this magnet all the way back here? No, it's because the paperclip is attached to the nail. The nail, just by being attached to the magnet, has become its own magnet. How? Because this magnet made all the domains inside of this little nail line up. And because all the domains inside of the nail are lined up, well, then the nail becomes a little magnet. And that little magnet then holds on to this little paperclip, because then the nail makes the little paperclip into a magnet. And so the little paperclip becomes a magnet. And the same way that a magnet will pull on another magnet and they'll pull each other together, the same thing happens here. The nail becomes a magnet, the paperclip becomes a magnet. Now they're both magnets and they both pull together. And so the little paperclip stays. All that you need to make something into a magnet is another magnetic field. Now here's a question though, because students start to say, wait a second, Miss Wilson, you're saying all that I need to make something into a magnet is another magnetic field? But then they say, but not everything can be magnetized. For example, here I have a little piece of copper wire. My copper wire, My copper wire doesn't stick to my magnet at all. In fact, if I hold them both up and then I drop them, then the copper wire will just fall. It feels no attraction to this magnet. So they say, Miss Wilson, if everything has atoms, and the electrons in any of those atoms are moving, then why can only certain materials become magnetic? And the truth is that not all materials can become magnetized. The only types of materials that can become magnetized really deep down are what we call ferromagnetic materials. Let me try again. Hang on. I want you to be able to actually read what I'm writing. So, it is working. Ferromagnetic materials. Okay, here's the truth, is that not everything can become magnetized very easily. Now, anything, if you put it in a magnetic field, it'll respond to that magnetic field and the domains will align slightly, but not everything is going to give you a really significant amount of domain alignment. That's because it really depends on how well the electrons can change their spin or change their direction within that substance. So some substances, some materials let their electrons change their domains really easily, or change the orientation of their domains, change the orientation of their dipoles really easily. Other ones, not so much. So it really just depends on the material. The type of materials that we say are ferromagnetic, in other words, materials that are able to be magnetized, they're very good at letting their electrons just spin the direction that the magnetic field demands that they spin, are materials like iron, nickel, and cobalt. Iron, nickel, and cobalt. Of these three, iron is the best ferromagnetic material. It is the best at being turned into a magnet. In fact, the name ferromagnetic comes from the Latin word ferro, which is the Latin word for iron. Iron is so good at becoming ferromagnetic materials that we named ferromagnetic materials after iron. Nickel is okay. It's not great, but it works okay. And then cobalt is also kind of okay, but iron is the best one here. There are also plenty of other materials that are ferromagnetic materials, but a lot of them are rare earth elements, and rare earth elements are not used as commonly to make magnets today, mostly because rare earth elements are rare, and so we don't have a ton of them. However, these are the ones that you'll normally see that we use to build magnets. These type of magnets that you see here, these type of magnets you'll see all the time. They live on your kitchen fridge. They're totally great. And these type of magnets are what we call alnico magnets. This is a little alnico magnet here. I bet you could probably guess exactly what an alnico magnet is made of. I'll give you a hint. It's 3 elements. An alnico magnet is made of aluminum, nickel, and cobalt. So you see that it's made of 2 ferromagnetic materials, and then you have aluminum, which aluminum isn't actually a ferromagnetic material. It's technically classified as a paramagnetic material. But the nickel and the cobalt here in combination really make this whole thing ferromagnetic, so that it can operate as a little magnet for you. The strongest type of magnets that we have are what we call or I should say the strongest type of permanent magnets, in other words, a magnet that can't be turned on and off. We'll talk about electromagnets later. But the strongest type of magnet that we have is what we call a neodymium magnet. A neodymium magnet. And a neodymium magnet is made up of iron, neodymium, and boron. And that is not the kind of magnet that you're going to be seeing to like hang stuff on your fridge, but it is a very strong type of magnet and one of the strongest types of magnets that we have built as a permanent magnet. So not everything can be turned into a magnet, but these ferromagnetic materials can be turned into a magnet, just depending on how willing they are to allow their electrons to go the way that they need to go. So that's a little bit on types of magnets and how to build a magnet. Let's talk a little bit about how to destroy a magnet. If you want to wreck a magnet, there are three ways. Three ways to absolutely obliterate a magnet or to demagnetize. There are three ways to demagnetize a magnet. So I have to move this little guy up here. Three ways to demagnetize a magnet. The first way to demagnetize a magnet is to jar the magnet. Literally, take the magnets and shake them like crazy. Or take the magnet and throw it on the floor. Or take the magnet and run it into a wall. Any of these kinds of things will actually demagnetize the magnet. Whenever I say that in class, students always like they want to take their little magnets and they want to hold them up in the air and shake it and then see if it's less magnetic. Yes, it actually does demagnetize it. I realized I just shook this as I was talking. Yes, it actually does demagnetize the magnet. It is not good for the magnets. It makes them less magnetic. The reason why is because all that being a strong magnet means is that your domains are all lined up. Well, if you are shaking the magnet, you can literally shake the domains out of alignment so that they're not as lined up anymore. And you can go from being strongly magnetized to being slightly magnetized or less magnetized just by jostling the whole thing around. So that's one way. Another way to do it is to heat it. If you heat a magnet, we know that heat is just kinetic energy. Hey, you get all those domains up and moving, get all those little dipoles up and moving. If those dipoles are moving, their likelihood of staying lined up is not very high. And so one way is to heat a magnet. That'll get everything nice and jostled up in there. And then the last way to demagnetize a magnet is to place a magnet in an opposing magnetic field. If you place a magnet in an opposing magnetic field, well, you know that magnetism is contagious, and what will happen is that those two magnets will undo each other. Like if I place this slightly magnetized magnet here next to another magnet, let me grab another color. Let's try green. Okay, 1 second here, team. So sorry. Okay, if you place this magnet next to another magnet like this one, and this one has all of its domains going this way, like this. Well, what will happen is these domains will say to these domains, hey, get lined up and start going this way. And these domains will say to these domains, hey, get lined up and start going this way. And they'll fight each other, and they'll actually both undo each other, so that at the end, the magnets will both be less magnetic than they were at the beginning because the magnetic fields are trying to undo each other. This is why we have to be very careful about how we store magnets. At a school that I worked at before I worked at this school, I went up to the administration and I said, hey, I would really love to do a unit on magnetism. Do you have any magnets? And they said, oh yeah, for sure. And they brought me down into this back corner of the basement. And in the back of this room, in the back corner of a back room of the basement, they took out a little cardboard box, and inside of that cardboard box was a Ziploc baggie that was full of magnets. And I looked inside that Ziploc baggie, and I took out one of the magnets, and I took that magnet, and I held it up to a paper clip, and guess what happened? Nothing. Because all of the magnets had been sitting in a Ziploc baggie together, demagnetizing each other over time, sitting in the back corner of a basement room, demagnetizing each other in a Ziploc bag. We have to be careful how we store our magnets. If you store your magnets so that their magnetic fields are opposing each other, they will gradually demagnetize each other until those magnets aren't magnets anymore. They're just iron. However, you can remagnetize a magnet if you need to, but all you have to do is place it in the presence of a strong magnetic field for a good amount of time. If you place a ferromagnetic material in the presence of a strong magnetic field for a good amount of time, then that thing will get right magnetized again. So that's the story. Fun facts. Okay, last thing that I want to talk about, actually, whoops, two more things that I want to talk about today before I leave you. The first thing I want to talk a little bit about is what are magnets like? So I'm going to pull up a new page here. Let's talk a little bit about the characteristics of a magnet. Now these are mostly things that you actually probably already know. A magnet, wait, let's go back. I want this a little bit longer. A magnet always has two sides. We say that a magnet has a north pole and a south pole. Now, the reason why we say that a magnet has a north pole and a south pole is because long ago, before we even knew what magnets were, there once was a sailor who found a magic rock. And the sailor found this magic rock and it became his pride and joy because he would take this magic rock with him on his journeys on his boat. And he would take this magic rock and he would tie a string around the magic rock. He would hang it up like this, and he would say to all the other sailors, watch how magical my magic rock is. And they would say, I don't understand what's so magical about your magic rock. But as they would sail, the magic rock would turn on its little string. And it would turn so that one end of the magic rock was always facing the north pole of the earth, and the other end of the magic rock was always facing the south pole of the earth. And so the sailor said, I have a magic rock that we can use to navigate. It'll show us where north always is. Nowadays, we know that the magic rock that he found was a magnet. It was a naturally occurring magnet. And we also know that what he had discovered, what he had invented, was what we call a compass. A little magnet that always points north. Now, because he had his magic rock and because one end pointed to the north end of the earth, he said, that end of the magnet I shall call, or that end of the magic rock I shall call the North Pole because it always points north. And he said this other end of the magic rock, which always points south, I shall call the South Pole. And so that's how we got the names, is that they're named after the way that they point on the earth. So the North Pole of a magnet always points to the North Pole of the earth. The South Pole of a magnet always points to the South Pole of the earth. Now, there's some ways in which norths and south are kind of reminiscent of positives and negatives, but they're not entirely the same. Here's a way in which positives and negatives are different. You can absolutely have a little positive charge sitting all by itself. We call that a proton. It totally happens all the time. You can also have a little negative charge sitting all by itself. We call that an electron. It's very common. But you can't have a little north sitting all by itself or a little south sitting all by itself because north and south are like sides. It's kind of like saying, like, here I have the right side of this magnet, and here I have the left side of this magnet. It's kind of like if I were to say, hey, could you have the right side without the left side? And you would say, kind of, but also no. And here's what you could do is you could say, okay, well, I'm going to cut this thing straight down the middle, cut this thing in half. And so now I don't have one magnet anymore. Now I have two magnets. And one of my magnets is all the right side, and the other magnet is all the left side. And so you would say, well, here's my right side of my magnet, and here's my left side of my magnet, but check it out. Doesn't this new magnet now have a right side and a left side? And doesn't this new magnet now have a left side and a right side? So you can't have a right side without a left side. If you have a right side, you also have a left side. And so it's the same thing with norths and souths. If you have a north, you also have a south, because the south is just the end that's opposite of the north. And if you have a south, then you also have a north, because it's just the end that's opposite of the south. So you can't break a magnet down into like only a north or only a south. That's just as ridiculous as breaking down something into only a right side and only a left side. So that's a little bit on norths and souths. You also know a few other things about norths and south. This one is similar to electricity. You know that like poles repel and opposite poles attract. If you put a little, I'll try to draw these kind of quick here. If you put a little, here's a north, here's a little south, and you put a little, here's a north, here's a little south. If you put two magnets facing like this, these two magnets would push away from each other. They would be repelled. And you can do this too with your magnets. You've known this since you were a child. You flip the magnets this way and they push apart from each other. They don't like each other. But then you flip it back around and they pull towards each other. They do like each other. That's because likes repel, but opposites attract. You put a little south next to a little north, and here's my little south over here, here's my little north over here, and those two will pull towards each other. If those two pull towards each other such that they become one magnet, well, now you just have one new magnet that just has one south side and one north side, like this. So we see that north and north don't like each other, they'll push apart. South and south don't like each other, they'll push apart, but north and south will pull together. This is very reminiscent of what you see with charges, likes repelling and opposites attracting. Now the next thing that you need to know, wait, let me make sure that I got all the details. Oh, yes. Okay, yes. The next thing that you need to know is that we can draw magnetic fields the same way that we drew electric fields. And let me draw a little picture here of a little magnet. I'm going to actually make it a little bit bigger here. Here's a little magnet. This magnet has a north pole and a south pole, and we can draw magnetic field lines the same way that we drew electric field lines. When we draw magnetic field lines, we always draw them the way a little north would go. You remember when we drew electric field lines, it was always the way a little positive would go. Well, in this case, it's always the way that a little north would go. Well, if a little north saw this north over here, it would say, no, thank you, and it would run over this way. If a little north saw this north over here, it would say no thank you and it would run away, but then it would also be pulled in towards the south on the other side, and so it would curve around like this. Likewise, a little north over here would get pushed away from the north, but then pulled back towards the south this way. And a little north placed right here would get pushed away from the north, and oh gosh, wait, I don't like how I drew that. So sorry, team. Thank you for your patience. Away from the north and towards the south like this. And away from the north and towards the south like this. And you could imagine that we could have like even bigger loops going around. Now, the truth is here that actually magnetic field lines, in contrast with electric field lines, are always drawn as circular loops. In other words, it doesn't end here, but it actually goes all the way through the magnet like this and connects back with itself here. Same thing with this one up here, it would go all the way through. Oh, wow. Thank you so much for not finding any threads. I do appreciate that. It would go all the way around and connect back. This one here would also go all the way around and connect back like, oh gosh, not like that. Like it would actually connect back, not like the way that I drew it. It would go all the way around and connect back like this. And this one here would go all the way around and connect back like this. So we see that magnetic field lines are actually closed loops always. They are not open loops. This is because you always have a north pole and a south pole. So it's always running away from the north and back to the south. Now here's what's interesting, and here's where students get confused, is on the outside of the magnet here. So here's my magnet. On the outside of the magnet, do you see that the arrows are pointing away from the north and towards the south? But on the inside of the magnet, they actually point south to north. The way that I like to remember that is I like to imagine which way would a little north go. Well, a little north would get launched through this magnet, and it would want to go to the north side because that's where the norths live. But then if it made it on its way out, then it would get zipped back around to the south side, and then it would get launched up back to its home again. That's kind of how I think about it. That's one way to think about it. A few things to note here. First is that the direction of the arrow shows the way the little north would go if it were outside of the magnet. And second, that the density of the arrows shows the strength of the magnetic field. You'll notice that the arrows are way more dense inside of the magnet. That's because there is a magnetic field inside of the magnet, because the magnet is made by moving charges. And so the magnetic field is stronger inside of the magnet than it is outside of the magnet. So that's a little bit about how we draw magnetic field lines. There is a lot of practice that you get with that in your lab experience. So you'll be able to draw magnetic field lines between, like, if you had a north here and a south here, and then you had another north here and a south here. What would those magnetic field lines look like between those two magnets? So that's something that you'll get a lot of practice with. So there is a little bit on what magnets are like and how to draw magnetic field diagrams. The last topic of the day for today is a little bit about the Earth's magnetic field. The Earth does have a magnetic field. That is why all compasses work. That's why the sailor's magic rock was magical. is because the Earth has its own magnetic field. So here is the Earth. Okay, well, close enough. Here's the Earth. Here is the Earth's, I'm going to draw a little line here. Here's the Earth's axis of rotation. That is not great. Let me try again. I'm so sorry. I'm so sorry. I just do feel really sincerely embarrassed. Oh, well, okay. Maybe not. Okay, I guess, never mind. I suppose I am starting all the way over. I was too, like, trigger happy when I was clicking the undo button. I was too undo happy. It's okay, that Earth is so much better. Can we just all agree for a second that that is a good looking Earth right there? Okay, and now let us draw the axis of rotation of the Earth. We'll draw it like right here. It is, you will notice, at a slight angle there. This up here is what we call the geographic North Pole. We'll talk about why we call it the geographic North Pole in a second. And then down here we have what we call the geographic South Pole. Now, here's the truth, is that a little sailor had a little magic rock, and he said, my magic rock, the North Pole of my magic rock, of my little magnet, always points to the north, so I shall call it the North Pole. And the south end of my magnet always points to the south, so I shall call it the South Pole. But the reality is that things are a little bit more confusing than that. If a little magnet is lined up so that the north end is facing a certain point, and it always faces that certain point, and the south end is facing a certain point, and it always faces that certain point, well then, this point right here has to be a South Pole, and this point right here has to be a North Pole. The reason for that is because norths are pulled towards souths. North and south like each other, and souths are pulled towards north. If you had a, let me try again. Oh, wow, it just got dark in here. I wasn't moving enough. If you had a North Pole right here and a South Pole right here, like this, set up here, then a South Pole, oh, thank you so much. A South Pole would be pulled towards the North Pole. You would never have a little magic rock swing so that the north is facing the north because it would be repelled by the north. No, it would swing so that the north is facing the south. So if our sailor's magic rock, if the North Pole of our sailor's magic rock was pointing to the geographic North Pole of the Earth, that means a few things. First, it means that the Earth kind of actually acts, whoa, not like that. Try again. The Earth, oh gosh, not that much. I keep being so like undo happy. Okay. The Earth acts like a giant magnet because only magnets pull on magnets. So the reason why the Earth was pulling on his magic rock is because the Earth itself is a magnet. Let me draw it here. I'm so sorry. I'm just trying to draw it like really exactly how I want it to be, and I'm just not really nailing it, but that's okay. I'll just describe to you what it's supposed to look like. Okay. So here's our little magnet. Now, if his little magnet, if the North Pole of his magnet was pointing towards the North Geographic Pole, and the Earth is a giant magnet, that means that the North Geographic Pole of the Earth is where the South Magnetic Pole of the Earth is, because only a south would pull on a north. If the south end of his magnet was pointing towards the South Geographic Pole, that means that's where the North Magnetic Pole of the Earth is. So if the Earth is a giant magnet, then the South Magnetic Pole of this giant magnet is located by the geographic North Pole of the Earth. And if the Earth is a giant magnet, then its North Pole is the North Magnetic Pole. Is located where the geographic South Pole is. This is very confusing, and it would have made it much simpler if we just didn't call one end of the magnet north and the other end of the magnet south, and that would have lined everything up and everything would have been fine. But as it is, here we are. So we say that the Earth is like a giant magnet with the South Magnetic Pole at the geographic North Pole and the North Magnetic Pole at the geographic South Pole. And we say approximately at the North Pole because it's actually off by about 9.5 degrees. So you can see I try to draw this a little bit here so that this is kind of like straight up and down and this is at a slight angle. It's because the magnetic pole is slightly off from the geographic pole. It rotates on an axis, but the magnetic pole here is 9.5 degrees away from the geographic pole. A few things that are true is students always ask, wait a second, Miss Wilson, if you say that magnets are caused by moving charges, then why is the Earth a giant magnet? Well, that's because the outer layer of the Earth's core here, the Earth's mantle, is made up of like molten rock. And that molten rock here in the middle is just constantly swirling around and moving like crazy. And if you have a ton of swirling metals in here, then you have a ton of swirling electrons. And so if you have swirling electrons, well, you got moving charges. If you got moving charges, then you can create a giant magnetic field. So that is why the Earth kind of acts as a magnet. And the magnetic field of the Earth is actually very, very helpful to us. It protects us from all kinds of radiation from the sun that could be potentially dangerous. And it also creates the northern lights that you can see in the wintertime if you live in Alaska. So that's a little bit about the Earth's magnetic poles. Please double check and make sure, check in your brain, do you understand why the geographic north is where the magnetic south is? Why the magnetic north is where the geographic south is? Also, go back and refresh your memory on all the things that we talked about today. Do you understand how magnetic field lines can be drawn? Do you understand why we always draw them from north to south? Do you understand the difference between a north pole and a south pole, how they can't be separated from each other, but there's always a north pole and there's always a south pole for every magnet? Do you understand the rules of attraction and repulsion for magnets? That north and north don't like each other, south and south don't like each other, but north and south do like each other. And then also, do you understand, wait for it, how magnets get created? How magnets are created when dipoles get lined up, and then that creates domains, and then magnets are created when domains get lined up, and the more lined up they are, the more strongly magnetized something is. Also, do you understand the difference between ferromagnetic materials and non-ferromagnetic materials? Do you understand the two types of magnets that we talked about, alnicomagnets and neodymium magnets? Do you understand the 3 ways to demagnetize a magnet and also how to remagnetize a magnet? And also, just really making our way back through history here. Do you also understand that magnetism is caused deep down by moving charges, and that moving charges in little atoms can create dipoles? And those dipoles, those one atom big, tiny, teeny, tiny magnets created by their little electrons spinning around, then those are what combine to create domains. And then those, if they get lined up, then they can actually create magnetic materials. And that is an overview of everything that we talked about in this video. I hope you have a wonderful, wonderful rest of your day, and we'll see you next time to talk a little bit more about magnetism and magnetic fields. See you, people.